Hi guys, welcome to my video on power and radical functions. So we're going to be talking about what a power function is and also what a radical function is. And more specifically with power functions, looking at the end behavior and how we can get that just by looking at it. And then we're going to look at how we can convert from radical to exponent form. Okay, so let's go ahead and get started. A power function is just super basic. A power function is a function with a power, x to the power of 3. That would be a power function of degree 3. Okay, another example of a power function could be this, where there can be a coefficient in there, and that would be a degree 2 power function. We would call this one quadratic, and this one cubic. Quadratic. Okay, we've already talked about those in class. Let's look at some different ones. Let's throw in a negative there. Negative 10 x to the power of 5. This would be a degree 5 power function. We don't really have any other examples or any other names for degrees past 4. We can call it quartic or quintic, but you're rare to see that. So let's say degree 5. So in general, a power function can be represented like this: a times x to the power of n, where this would be a degree n power function. So what I want you guys to pay attention to as you continue watching this video is I'm going to describe what end behavior is in just a minute, and I want you guys to connect how the degree and this number in front we call the lead coefficient, right? Coefficient number in front, the lead one, because well, it's in front of the highest exponent. We'll talk about why that's called that later. But right now, there's only one coefficient, right? So how does the degree and the lead coefficient dictate or relate to the end behavior? That's what I want you guys thinking about as we progress. So let's go ahead and talk about what the heck is end behavior. So the end behavior function, a formal definition would be the behavior of a function on the extreme values of x. Well, what are extreme values? Extreme values being really big and really small values, so positive infinity and negative infinity. So basically, the layman's terms is to say the end behavior is the behavior of the function at the ends. And what do I mean by the ends? Well, let's talk about what the ends are. The ends would be the left end and the right end. So for now, we'll get into more specifics later, but all we need to know is, where's the function going? Is it going up on the right? Is it going down on the right? Or is it going to a number on the right? And we're just going to worry about up and down for now. So what's happening on the right? What's happening on the left? So let me show you some examples. If I wanted to find the end behavior of the, let's say, sketch end behavior of this function of f of x equals x to the 5th. Well, x to the 5th is going to look something like this, where it has super flat area right here, and then it goes back up. Oops, sorry guys, let me show you real quick. Okay, so this is x to the 5th. So we can see the end behavior based on the arrows. The arrows really tell you, the arrow on the right and the arrow on the left tell you what the end behavior is. So the end behavior is this. It goes up on the right and down on the left. That's all we need to worry about right now. We're going to get to more specific ways to represent that, but all we need to say is up on right. All we need to recognize is this. And down on left. If you guys can do that by the end of today, then you're golden. You've taken everything I need you to take out of this lesson. Okay, so let me give you an example of what I need you guys to be able to do after this video. So sketching end behavior, you're going to use a graphing calculator to sketch the end behavior. Let me see if you can see that now. The end behavior of each function below. All right, so y equals x to the 5th. What I want to do, since you've already downloaded Desmos, is I want to go to Desmos, and I'm just going to type this in. I'm not going to sketch the entire function. I'm just going to sketch the end behavior. So On the left, is it going up or down? On the right, is it going up or down? And that's all I need to worry about right now. So if I type in 5x cubed, this is what I get. So what's going on the left? It's going down on the left. So I can just put an arrow down there. It doesn't have to match exactly the steepness there. Just make sure it goes down on the left. What about the right side? It goes up on the right side. So I'm going to put an arrow up there. There we go. I've sketched my end behavior. I can move on to the next example. So let's go ahead and move on to our next example. I have negative 10x to the 7th. I'm going to go back and erase what I have here and plug in negative 10x to the 7th. X to the power of 7. So what do I notice here? Well, it's not the same as the previous one. It looks like it's almost inverted. So now I look at the left side. It's not going down anymore. It's going up. So again, I'm going to go ahead and put an up arrow right here on the left side. And then on the right side, it's going down. So I'll put a down arrow here. And that's it. That is the end behavior of this function. I don't care about what's happening in between right now. All I care about is the end behavior. All right, so I've gotten ahead of this one. I plugged in y equals 7x to the 4th, and I noticed kind of like a U shape, kind of like parabola, where it goes up on the left, and it also goes up on the right. Again, that didn't have to be as steep as we need it to be. And then finally, let's go to the last example. I'm going to do negative 18x to the 6th, and I notice that it goes down on the left and down on the right. So those are my end behaviors for those 4 examples. So what I want you guys to think about now is, what connection can you make about the sign of the function and the degree of the function with its end behavior? So in other words, how does this sign, positive or negative, and this degree affect the end behavior? Think about that for just a little bit. Try to write down a hypothesis. So now that we've talked about end behavior, let's go ahead and jump right into the radicals. So a radical, you've seen them before. They're just symbols used to indicate a root. So if I wanted to say, like, let's say cube root of x or square root of x, that would be called a radical symbol, right? It is often convenient to convert radicals to their exponent form, which I've shown you right here with this x to the power of 1 over 5, okay? So let me show you some examples of using it with numbers, then we'll go variables, and then we'll go to the general form. Okay, so you guys need to convert back and forth between these. So if I wanted to say, let's find the cube root of 27, that would be the same thing. Well, first of all, we know cube root of 27, what number times itself 3 times gives me this number inside. So the 3 comes from this. What number times itself 3 times gives me 27? 3 times 3 is 9 times 3 is 27. So I know that this should equal 3 because the cube root of 27 is 3. But if I wanted to rewrite this in exponent form, I would write this as 27 to the power of, well, when I look at the powers, the number inside, the exponent inside stays on top. Well, there's no exponent for 27, so we're going to write a 1 in its place. And the one outside the root goes on the bottom, 27 to the 1/3. So when I plug in 27 to the 1/3 into my calculator, I should get 3 because I already know that answer. So just to make sure we verify, if I want to find 27 to the power of 1/3, I get 3. Sorry, my screen's a little cracked there. But 3 would be that answer. Okay? If I wanted to do the same thing with square root of 81, well, I would get, I know the square root of 81 can be written as 81 to the power of, again, the exponent is 1 on the inside. And then since there's no number out there, whenever there's no number, we assume it is a 2. It is square root is what we start with, so that's why 2 is where 2 does not have that number. Okay? And we know the square root of 81 is 9, because 9 times 9 gives me 81. Well, let's see what 81 to the 1/2 power is. It should give me the same thing, remember, because it's the same way to write a different equation. And I get 9 as my answer. Let's look at something that has an exponent on the inside. So if I take the square root, remember square root because there's no number out there, square root of 2 to the power of 4, this is the same thing as 2 to the power of, my exponent inside is 4, that's going to go on top, over 2, which is going to go on bottom. Now I can totally plug this into my calculator, and I'm going to get 4 as an answer. Okay? So 2 to the power of 4 over 2 is going to give me 4. That's cool. But if I were calculating this without a calculator, I would want to simplify 4 over 2 to get my new exponent of 2. Well, 2 squared, we all know, gives me 4 as well, so I was able to solve this answer. Okay? So that's how you'd rewrite it if it's a number. It's the same thing for variables. So if I were to rewrite the cube root of x, I would rewrite this as x. Well, what's the power inside? It is 1, so that goes on top. What's the root outside? 3, so cube root of x can be written as x to the power of 1/3. If I look at square root of x, I can rewrite this as x to the power of, my exponent inside is 1, my root is 2, so x to the power of 1/2. And then finally, if I had the fourth root of x cubed, then I can write this as x to the power of, what's the number inside 3, the number outside 4. Okay, it's going to be super important to go from this form to exponent form, from radical to exponent, and then back over as well. So in general, for all equations, if you have the nth root of x to the power of m, then you can rewrite that as x to the power of m over n. If you want to think about it, it goes top in, bottom out. Okay, so top, well, the inside goes on top, the bottom goes outside. If you're looking at the other way to do it, so I could say, or if I want to convert from exponent to radical, that is also x to the power of m over n, I don't need to write anything else there. That can also be done by using top in, bottom out. Well, what's on top? The x to the power of m, that m is on top, and then what's on bottom? The n is on bottom, so that goes out. So top in, bottom out. And that's how you would generally convert any expression from radical to exponent or from exponent to radical form. And that's all I got for you guys today. So make sure you get these focus notes done by next class.